Okay, good. So I'm gonna set up the whole central force thing, and we made it to the effective potential last time. We said something about circular orbits. So we'll work our way through that again, and then we'll actually continue on, maybe the Kepler problem today, definitely by Friday. Okay. So for the central force formalism, and once you've seen this a few times, it'll make a lot of sense, and we can take it through from the top, so to speak. So if you're going to start with Newton's law, in this very general form, then what we're saying in this case is that the force that we're looking at has the form as this form, okay? And this is the distance from the origin, right? And so that's a special case, right? Obviously a very special case. If you have a force of this form, you then have a potential energy of this form here. And if you have a potential energy function of that form, then you have conservation of energy. So then energy is conserved with 1/2 m vector r dot squared plus u of r is equal to E is constant. So that all follows from having a central force. Then there could be a digression that this would just be the formal problem of a central force with respect to an origin. But of course we had something like this from the two-body problem as a single dot there, right? So I'll just put a note here. When you had two bodies, with if you had two bodies with a force that was directed along the line, okay, so this was M1 vector R1. This was M2 vector R2. So yeah, if you had the force along this line joining them, then you were able to create this relative vector R, R1 minus R2. Okay, it's a little messy. And then you were able to show that this two-body problem reduced to a one-body problem. Okay. So we had two-body problem, reduction to one-body problem with M, the reduced mass, plus M2. So we had that, and I'll even just write down for the record. And then the R1 was equal to M2, M1 plus M2. That lowercase vector R2 was equal to negative M1, M1 plus M2. Like that. Okay. So now you have a reduction to this one-body problem. And you would say, you've got M R, the second derivative is equal to, and so that's where you've landed. And you don't have to worry about whether it's two bodies or one body. You just have this formal problem solved. That was fine. Okay, so then we continued on, and we had angular momentum, and we found that that is also conserved. Angular momentum is conserved. And that angular momentum is L equals R cross M R dot. We'll write it that way. And once you know that angular momentum is conserved, then you can say motion is restricted to a plane, and that motivates the use of the plane polar coordinates. Right? So when you see this all at once, you see it, the whole logic really flows, right? Angular momentum is conserved, and therefore we have motion is restricted to a plane. And therefore we use plane polar coordinates, and we have to learn something about those. Plane polar coordinates, and you know, you start with this: x equals r cos phi, y equals r sine phi, and then we found that vector r can be this r times the r hat. R dot can be R dot R hat plus R E dot phi hat. And that was actually enough to evaluate this thing in plane polar coordinates as well. So yeah, we have all that in our notes, and you know, anytime you go back and review it, you'll just see it making more sense. The logic here is really nice. So then what we did was we took this understanding and went back into the energy. So that's our next step. I'm going to erase all this stuff. We go back into the energy, and we express the energy in terms of these plane polar coordinates. And that'll bring us right up to where we were last time. Go ahead and erase all this stuff. Okay, so we have the energy with all of the discussion that goes into it. So we have a half m dot squared u of r equals E. That's the energy, and this is before I implemented the plane polar coordinates, the energy. And again, whenever I square a vector, it's just the dot product with itself. So we end up with, when we use the plane polar coordinates, we end up with 1/2 m r dot squared plus r squared e dot squared plus u of r. So we can drop the vector here because it's just the separation distance, u of r equals E. So that's energy, plane polar coordinates, and angular momentum. We have m r squared phi dot was equal to the magnitude of the angular momentum. Angular momentum was a vector, the direction being constant restricted the motion to a plane, and the vector being constant meant the magnitude was also constant. And the translation of the magnitude in plane polar coordinates gave us this. Just from the stuff I had just erased over there. Good. So now you have two first order differential equations that are coupled. There are two quantities that we have to solve for, r and phi, and we have these two coupled first order differential equations. So let's write that down. Coupled first order differential equations. And since Newton's law is second order, just erased it. This already represents one integration of Newton's law. So the next step in solving these is to take this conserved quantity. Actually, just make sure your angular momentum is constant. Right. led to, and this is where we ended last time, that ended with 1/2 m r dot squared plus L squared over 2m r squared plus u of r equals E. So this is now a first order differential equation, one variable. And you know, we could retain this one here, and then we have, and you know, m r squared p dot equals L. That's our second order equation. But now we can just focus on this one. And this came from the kinetic energy. But what we do is we group these together and refer to them as the effective potential, U effective R. And then what we have, in essence, is the one-dimensional plus U effective of R equal to E. The one-dimensional problem, we can just use all our skills and techniques on this object here. Of course, when you're done solving for this, then you could, if you wanted to know the phi motion, you'd take that as a known quantity, and now you have this differential equation of phi, right? You could literally integrate it with phi. So that's the plan. So let's look at an effective potential and graph it. Effective potential, and see how far we can get. Only defined for positive R. And we'll immediately look at Newton gravity. In this case, we have, we're just going to write U of R is minus alpha over R. Alpha is a positive quantity. And we can always put in what its value is, but for simplicity, we just write minus alpha over R. And then that's for any attractive central force potential. And in fact, if we let alpha be positive or negative, we'd also have repulsive forces come out of that. So this is good. And what is this effective potential? The effective potential is L squared over 2mr squared minus alpha over R. So we have to graph this thing to really see what's going on. And we just graph them individually. We have a 1 over R squared. Something like that. And we have a minus 1 over R, which looks like that. So how do we add those two to get a reasonable result? To add these two, we have to look at the limiting cases. So for very small r, 1 over R squared will dominate. Okay, for very small r. So that means the sum of these two is going to come down from here somewhere. But for very large R, this will vanish faster. So for very large R, this one will dominate. So that means it's going to come out to here somehow. And so it ends up negative, starts out positive, so it's going to have this generic shape. This is nicely exaggerated, but it shows everything we need to know. Okay. So yeah, there's the shape. It has everything going on. We're going to do a couple of other different effective potentials. But this is the actual Kepler problem effective potential. And you see it has a local minimum corresponding to a certain energy, which I'll call E sub 0. And look sub 0, right, then the E on this side and what's here on the red line, over the red bracket are the same. That means R dot is 0. This is the same argumentation you have with one-dimensional motion in general, and that means you're just sitting there at rest at the bottom of that effective potential. Stable equilibrium. Of course, in reality, you're here at R sub 0, and if there's any angular momentum, you know, you have a constant phi dot, right? And that's a circular orbit. So we already have, that's how these analyses go. So for U effective R sub 0 equals E, let's call it E sub 0, we have R dot equals 0, and that means it's a circular orbit. So you get a circular orbit off that. So you can see the next step would be to have some energy, I'll call this E sub 1. And then, you know, you can imagine a particle moving back and forth in this potential well, and it has a minimum, come over to here, a maximum R, right? So this would be an R1 maximum value, and this here would be R1 minimum value. And because this is formally just a one-dimensional problem, what's the particle doing? It's oscillating back and forth. There would be a certain period integral that we can do. Everything that we learned before here. Of course, since it's an orbit, it means it's coming closer to the origin and going farther away from the origin, closer and farther away. And that's going to turn into an elliptical orbit, which we'll prove. Right now, we just realized that it'll be an orbit that comes closer and farther away. So, yeah, this sketch, make it pretty big, it's pretty rich in content. What we would have in that case for this E sub 1, we'd have 2 radii, and we'd have an orbit that goes from the minimum out to a maximum, back to a minimum again, and so forth. And you're saying, yeah, why didn't I close the orbit? For the ellipse, it will be a closed orbit, but for other potentials with similar properties, it won't necessarily be closed. But yeah, you know, I'll make this more of an ellipse for the first go around. Okay, so there's your minimum and maximum, and so as you go back and forth between R min and R max, right, those are the turning points at which R dot is 0. You're tracing out an orbit that goes something like that. Here's the center of the potential. Yeah, so that's what that means. Let's add one more energy to this. What does this one mean? Yeah, you're not going to have closed orbit at all.
It would be just sort of spiraling away.
Yes, because imagine a particle here, you release it from rest. Right? If it was a roller coaster, it's going to leave and never come back because it has that extra energy. And so that means it's approaching, this was its closest point of approach, and then it's going to go out to infinity. Or it could have come out from infinity, come in from infinity, reach that closest approach, and then go out to infinity again. So for this potential, those will be the hyperbolas, the hyperbolic unbounded orbits. And then you see really clearly from this graph even that the bounded orbits have negative energy and the unbounded orbits have positive energy. That's really important for the central force problem. Yeah, anyway, so we'll put that here as a note as well. Bounded orbits, E is less less than 0, unbounded, E is greater than 0. Good, so yeah, you see we can learn a whole lot just by studying the effective potential without having had to solve the differential equation, which we'll now tackle. Okay, the effective potential. Actually, we'll do another effective potential, just to have a few of them in here. So this was example 1. And then example 2 for the effective potential, we're going to let U equal just some K times R. So you have some linear potential. And then the effective potential is the one we want to study. We've always got the L squared over 2mR squared, K times R. We can graph that. Going to use the same technique we used right here. So this 1 over R squared is doing that. What does K times R look like? K is a constant.
Just a straight line.
Yeah, it's a
Starting
straight
here
line.
and then shooting out.
Go like that. And then you add the two. By the way, when you add two functions like this, here we were just winging it, right? But here you would say, okay, I've got the intersection of those two lines, so that double that score right there. That's definitely where the point, where the curve goes through, and you've got something like this, right? But again, you have a local minimum, and so this time you're only going to have bounded orbits, right? All the orbits will be bounded because this just keeps going. So for any finite energy, you're just somewhere up here. So in this case, our E sub 0 gives us the circular orbits. I'll just do an E sub 1. And what's nice about this example out here, okay, R sub 1 min and max, is it's clearly unsymmetric. Okay. This one was also unsymmetric. And I'll do one more, and we can make these a homework problem. Sort. So if we have 1/2 kr squared, so we can somehow harmonically couple these two particles together, and they're orbiting at the same time. And this graph this one I'm just going to do. I'm going to have this branch here, 1 over R squared branch. Let's go ahead and write this down to be effective. Equals L squared 2mR squared plus 1/2 kr squared, different k obviously. But yeah, we're going to have this branch here on the left, and this one's going to go up like a parabola. So we're going to have something that goes like that. And again, all bounded orbits, local minimum. And remember, these local minima are always circular orbit. So here's what we want to do for these, all 3 of these. We can do a couple of good things. The first thing, and then I'll write it all down. The first thing we want to do is get the frequency of small oscillations. Because if the energy, I made this E1 substantially greater than E0. If the energy is very close to E0, just a little bit more, then we're looking down at, we're looking over at a quadratic potential well, and our whole theory of small oscillations comes into play. So we can just knock it out, right? We just get the second derivative having located the first derivative minimum. So we'll do that, but what kind of an oscillation is that? It's a harmonic oscillation, but it's an oscillation in this R, in this radius as the thing orbits there. So for a closed orbit, the period of that oscillation is going to have a certain relation to the circular motion itself.
So in orbit is perfectly circular, the oscillation basically zero.
The frequency would be zero, and the period, yeah, would go to infinity. So that's, but yeah, that's always the first, that's the first, first derivative vanishes, second derivative gives you the frequency. So those would be small oscillations about the circular orbit. Small oscillations about the circular orbit. So we'll do those for all three of these. That's a good exercise. And we'll study them in more detail on this thing here. Yeah, so I'm going to formulate that right up here. So for example 1, 2, and 3, find R0 and omega sub R for all three of these. And of course what that means is U effective prime of R0 is equal to 0. That's your criterion for finding R sub 0. And omega sub R is equal to U effective double prime evaluated at R sub 0 divided by M square root. So those are the things you're doing. Go ahead and include a nice labeled graph and everything, nice picture in your presentation of this. And we'll use those results later on as well. We can add something. IX. Fine. We could even find the period T, we'll call it, of the circular orbits. There we go. So you have all three of these examples. The period T of the circular orbit, that is going to come out of this expression here. The circular orbit is controlled by this expression. Because, I can even put this under here, so you have M R naught squared, and then this phi dot is an omega sub phi is equal to L, right? Because when R is constant, then phi dot is constant, and therefore that phi dot is what we call the angular frequency of the circular motion. So this is the one you can, T is equal to 2 pi over omega. That's how you get that orbital period out. And yeah, you can even compare these omega sub r's to the corresponding omega sub phi. And that at least gives you some interesting results as well. So all this is possible just using the effective potential. So in fact, after we do the full Kepler problem, we're going to come back to a deeper study of the nearly circular orbits that returns to just studying the effective potential. That's a pretty rich and cluttered picture, but there's a lot there, so write it out, in great detail. Good, so then we've studied these effective potentials and learned a bunch about them. So, yeah, once you find the R sub 0, you get the omega sub R like this. The period you get out of here, so I'll just connect this with an arrow over to here. we haven't even solved the differential equation yet. Okay? So these techniques are pretty good. So now let's set up for solving the differential equation. So I'm gonna erase all this, and we'll go back to this object right here. Maybe I'll erase the whole thing. Everybody got these pictures? Now we're gonna use that separation of variables technique on this object here. So next, we're returning to 1/2 m r dot squared L squared over 2m r squared plus whatever central potential you have there, energy, and E and L are constants in here, and M, of course, is a constant as well as a parameter. So now, separation of variables, we're just gonna do this in a couple of steps. So first of all, we'll solve for dr dt, and we'll do it this way, 2/m E minus u of r minus L squared over 2m r squared, whole thing square root. There's already some wisdom here. This is just a way to find, say, the end, the turning points. Right? When this vanishes, we solve for this being 0 to be the turning points, which we essentially had up there when we were discussing effective potential. Okay? That would be here as well. And we've got a plus or minus, though. What do they refer to? R increasing and R decreasing. And so the plus or minus have a meaning. And we can separate the variables the way we do. We can get dt equals plus or minus dr over our expression here, e minus u of r L squared over 2m r squared, L squared, square root. And we can integrate both sides. Here we would just say we have t. Here we would have to, I'll leave the bottom open there, and we would have a integration variable. So this would give us t of r. T equals t of r. And if you can set up a problem like this, you've reduced it, and we just did. It's called reduction to a quadrature. Now, our goal is to find we want to find r of theta and prove that the orbit is an ellipse, right? That's one of our goals for the Kepler problem, or the Kepler problem. So what we're going to do is convert this here. And we can have dr dt is equal to dr dt right? But this is dr dt, and the phi dot we have as one of those conservation laws. Okay. Because remember we have m r squared phi dot is equal to L. So we would have this phi dot dp dt is equal to L over m r squared. And we could just make that substitution over here. We would make it right here and then rearrange. And that is effectively just implementing the chain rule. Okay. Phi. The RDP. So that's the substitution we're going to make. So we'll have or phi del over mr squared is equal to our plus minus this whole business. And then we'll just rearrange p minus u of r. Actually, not yet. Parentheses minus L squared. 2mr squared. There we go. So we have the r's on one side and the l's on the other. I think we have a room right here. Put that in there and then have a little study of it. Okay, so what we're going to have is d phi on one side and dr. And I'm going to do it this way, L over mr squared, for a reason, that would be a proper fraction there. And then 2 over n minus u of r. So this is what we're going to work with. That is L squared, 2mr squared. We're going to work with this one when we finally do our integration. So in fact, let's go ahead and do this. B is equal to integral, we'll keep the plus or minus, that's fairly important. I can prime all these. If you don't prime them, it's understood, right? That this is the upward bound. So that's the grand integral that we're actually going to solve. Now for the general case, you can't just solve this integral, but it turns out for the Kepler problem, the Newton potential, you can. Bad as this thing looks like, it's going to turn into a big complicated inverse cosine, and we'll be off and running. There's a couple things we can do before that though. So here's the box right here. There are a couple of analyses we can do on this before we actually solve it, and then we'll do some clever substitutions, and it'll turn into something simpler. But one thing we can do with this, right, and this is phi of r, so if we can do this integral, which can be an inverse cosine for a couple problem, and invert it, right, then we'll have our r of phi of r of phi will have 4. What we can do before that though is just something actually pretty simple with these plus and minuses. So say you wanted to do this integral from r min to r max. That's a well-defined problem, right? R min to r max, and one of our problems there, r min to r max is going to be the same as r max to r min. Right? You just flip it and take the other sign. Okay, that makes sense? So one of them is receding and one of them is approaching. And what that means is that these central force trajectories are symmetric with respect to that. In other words, the shape of the trajectory as it goes from r min to r max is the very same as when it goes from r max to r min. So that actually comes right off of here. We put that into some kind of a note for us. Note, we'll call it this way, delta phi is equal to integral r min r max. I'll just say all that stuff. Right? Okay. So that's the angle that's swept out between r min and r max. Angle swept out between r min, r max, like we had on that sketch a little while ago. So that angle being swept out. You can even see from R min to R max, you take the plus sign. From R max to R min, you know, you get the negative value of the integral, but you take the minus sign, that makes it positive again. So that amount of angle is swept out. Equals minus R max R min of that thing there. So the picture of that is kind of the way I drew it a little while ago. Leave this up here for now. I'll sketch that picture. So now the idea is this: we have, we'll just do a larger version. We have the closest approach point is going to be right here, and between R min and R max, we sweep out. In fact, we can draw it this way: we sweep out a certain amount of angle. This is something we're actually going to study. It's going to get a name, but for the moment, I'll just write R min, R max. That. So this is symmetric. So on the way from here to here, this is this delta phi that I just put on the board. This is that delta phi that I'm talking about. And it's going to be exactly the same. And in my case, here we're not going to have a closed orbit, obviously. It's going to be the same angle swept out when we return back to R min, say right here. That'll be the same delta phi. So again, that comes from just at this level. You don't have to know what the potential is. Central force, that's a property of orbits. Okay. So find some better words to express that with. You know, this will be a good place. Any questions on this? So this will be a good place for us to stop today, because then on Friday we'll actually knock out this integration. And the three problems that I assigned actually they round out this little discussion pretty nicely. And then, you know, for next week I'll have us do something with this, but I think Friday we'll get the Kepler ellipses on Friday. And that's the, you know, the Kepler problem is really one of the most important problems in all of mathematical physics. That and the quantum mechanical Kepler problem, which is what? You guys know what the quantum mechanical Kepler problem is? It's the hydrogen atom, right? Which is orbit of an electron around a proton, except of course it's no longer a geometrical orbit, right? It's a different problem, but the formalism, when you take quantum mechanics, actually goes through all these steps. Like when you take quantum mechanics and study the hydrogen atom problem, they construct an effective potential. Okay, they analyze the effective potential, etc. Okay, so anyway,